whatever those numbers will give you 0 on variation. And so the Lagrangian, the statement is the Lagrangian is defined only to within an additive total time derivative of any function, any sensible function of coordinates in time. And we'll see in the case of some transformations how that can work out. So we're marching right along here. And now we get to the homogeneity of space. I need to give myself some more space where it's not infinite and homogeneous. So there's another subtlety that comes in here in all of these presentations of the discussion about the assumption of homogeneity of space and time. Now, what do we mean by that? We mean a lot of things, and we all are perfectly happy with them intuitively and so on, but when you think about it, it's not perhaps quite so obvious. In the extreme, the statement is that the laws of physics are the same here as they are near Betelgeuse or in the Andromeda galaxy or in some very distant galaxy or right at the time of the Big Bang. That the physics, certainly in space, but in fact in all details, is the same. And if someone were designing the universe and they designed a universe where that wasn't true, physics would certainly be a lot harder. And I'm not sure one could say that physics wouldn't be doable, but it would sure be different and might not be doable if it was chaotic and the laws of physics right here were not the same as the laws of physics on the other side of the world. I don't think we'd have a world. It turns out that there is a whole area of study that sort of has to do with this, and I probably will come back to this later, but the anthropic principle. Does everybody know what the anthropic principle is? Not everybody, but this is, I have to cut it short. The anthropic principle is the idea, there's variations on it, the weak and strong, all this sort of thing. And the idea is that the principles of the universe are rather a delicate balance. Yeah, thanks. Are rather a delicate balance, and that you can't fool with them very much, or the universe would not have been as we know it. Could it have been something else? Who knows? And of course, in the religious extreme, people say, well, God set it up this way so that everything is just the way it is. The weak extreme is to say, well, it is the way it is because it's one example and it is what we got. I've done a draw of one. You can't calculate much in terms of odds. But it is certainly true that you can't screw much with h bar and some of these constants without causing a good deal of disruption. So kind of in the background of all that is this idea of the homogeneity and isotropy of space. And so we assume that there is a system in which the laws of physics are simple. What it amounts to, comes down to, is that inertia holds, that there is a system in which you can put something to be at rest, and without interaction with other things, it will not suddenly begin to move. So there is one delightful little complication of this, which is that we know now from the Big Bang, so we're saying that to a pretty good approximation, this classroom, for example, is an inertial coordinate system. But you know it's really not, because we're on the world which is rotating, and the world is going around the sun. There's a little centrifugal force there, and the sun is moving within our galaxy, and our galaxy is moving within its cluster in the direction of the center of the Virgo cluster toward the great attractor in the sky. Who knows what the hell that is? And so there are all these kinds of motions, but we can measure our absolute motion these days to a very high precision relative to the cosmic microwave background. And we are going like hell, something like 600 kilometers per second in that coordinate system. We're going somewhere at a good clip. We're not sure where. But we can actually define the rest system of the universe, which is to say, at rest with respect to the flash of the Big Bang that we see arriving. A little blue shifted one way, a little red shifted the other way. And so you can define that. There is a rest system that's unique in the universe. What the hell that means in terms of our physics, we don't really know the answer. But it is something that flies against both Galilean relativity and Mr. Einstein's relativity as well. And that's why just further little cultural aside, you will hear people giving talks about seeking situations where there might be a revelation of Lorentz invariance violation of Lorentz invariance, which is to say that we would be seeing that there is being at rest someplace is physics-wise better than being traveling at very close to the speed of light. But as of now, there is no evidence for any such a thing. So as far as we can tell, space and time is homogeneous, and for purposes of this course, as long as all velocities are slow compared to the speed of light, 310 to the 8th meters per second, then you can forget about all that relativity stuff until later in the semester. So anyway, here comes some more of the magic. So the homogeneity of space and time, you say, well, this means that L cannot depend on R. So okay, throw out all terms that I can think of with R in L. But it could depend on V. Yeah, okay, it could depend on V. But can it depend on vector V? Could L depend on vector V?
Vector V depends on R.
Right. And it has a specific direction. And if it had a specific direction, then it would be a vector quantity. It would violate the homogeneity of space. So we say, okay, that's it. Then we're only left with that L is equal to a function of L of V squared. I notice that Mr. Landau leaves out of his argument here saying that it could be a function of a higher order term than V squared. But at least V squared, which is a scalar. Well, okay, if it's v to the fourth, then that's p squared squared. But it could be a function of that. So then, if we now say that that is indeed the case, then since there's no r in there, then this means that dl dr is equal to 0, and so those terms are going to go out, and we're left with just d dt dl dv is equal to 0. And so if dl dv is a function of velocity only, this implies that v is equal to a constant. And what did we just prove? This is the law of inertia. Kaboom! Ta-da! Pull out the cloth. And so you can make a detailed argument about changing inertial frames and so on. And I'll just read his statement. There is not one but an infinity of inertial frames moving relative to one another uniformly in a straight line. In all these frames, the properties of space and time are the same, and the laws of mechanics are the same. And this is the Galilean principle of relativity. The modification that we'll make to that when we get to considering Mr. Einstein is that we will have to say that that's true as long as the velocities are small. When the velocities are larger, another one of those great simplifications for Mr. Einstein is you simply say that there is a maximum velocity. In fact, that's all you have to do when you get all the Einsteinian relativity. So, yes, and I had note the statement here. The complete mechanical equivalence of the infinity of such frames shows also that there is no absolute frame of reference which should be preferred to other frames. But Mr. Landau didn't know about the CNBR. It doesn't change the story, but it certainly should worry one a little bit.
In what considerations is the frame with a cosmic microwave background preferable? I mean, because you have.
It's the only one we got.
Well, I know it's the only one we got, but it's.
Well, I mean,
you have all of this valid in any inertial frame.
Yeah.
Yeah, you can define that this by principle of we're in the universe. This is the most absolute we have in the universe. Is there any advantage to choosing that frame? Are there certain situations where that's advantageous?
But not as far as we know. No. But it is. I mean, doesn't it worry you a little bit to know that there is such a frame? So you have to start to worry, for instance, that at its super high energies, where the relativistic gamma factor, which is the number of times that the energy is the rest mass of the particle, gets up to, or the energies involved get up to something called the Planck mass. Too far ahead, but when you get to those extremes where we know something has to break down, that probably starts to count. That is not, however, our concern around here or with energy, any energies that we're presently able to access, except maybe PCORM with the Anita experiment getting near the end of the cosmic ray spectrum. It's getting up there, but still not there. So, okay, and also in this discussion, so that we can change to another frame, r is equal to r prime plus some v, big V, t, the velocity of another frame, and that t is equal to T prime. And as you know, this falls down when we get to worrying about relativity. But for most purposes, here T is equal to T prime in Beijing and in Moscow, and for us pretty closely. But it is not true everywhere. The GPS system, as I'll remind you several times when we're talking about it later in the semester, the GPS system that everybody has in their car or sometimes on their watch uses actually relativistic and general relativistic corrections. So this stuff is not totally irrelevant, but for most things it is. Oh crap. Well, I'm almost there. Okay, the Lagrangian of a free particle. Well, this is important. Yeah, I can't escape this too much. The argument is that because this is where mass comes in, we can write L of V prime squared is equal to L of V squared plus dV squared L times 2V dot epsilon. Oops, I skipped a little bit. It's where I was going to write V squared, V prime squared is V squared plus 2V dot epsilon plus epsilon squared. That's substitution. And then I can expand that out. So I can, if I then go ahead and write L is equal to something times V squared, let's suggestively take something to be 1/2 M. Although, of course, you wouldn't guess that if you didn't know any better. So if we say that let L is equal to 1/2 mv squared, and so L prime will be equal to 1/2 mv squared plus mv dot big V, little d dot big V, plus 1/2 m big V squared. And this, then I can rewrite this term here as a total time derivative, dt of mr dot v, big V, plus 1/2 m big V squared t dt. I can write that as a total time derivative. And since we already showed that you can add any old function that's a total time derivative to the Lagrangian and it doesn't change anything, we can therefore get rid of that. And we see that in the simplest form, although you're free to add it, in the simplest form, L is going to be simply the sum of all the m a v a squared, where this is summing over some ensemble of particles. Now notice these are still, we're dealing with point particles. We haven't put in any external forces and so on. And we do that next. So M is you say, oh, of course, everybody knows M is the mass. You didn't know that M was what we call the mass. And in fact, there are many different things, not many, there are 3 different things that we mean by mass. And we'll have to talk about them. There's mass as the source of the gravitational field, the coupling constant there. There's mass, the inertial mass here. And there's another term that we can talk about in gravity. But for here, this is the inertial mass, and it is a constant. It has some dimension. We have lots of intuitive understanding of what it means, but from here, it's just the constant that appears out front of v squared here. And the 1/2 is superfluous, just to make things pretty. Because when you take the derivative of v squared, the 1/2 goes away. By the way, can the mass be negative? If the mass is oh crap, time again. If the mass is negative, then there won't be a minimum. And it can go on down to minus infinity. So this is the standard argument of why you can't have negative inertial mass. I didn't say anything about attractive gravity or anything like that. No mention of that at this point, right? This is inertial mass. So negative inertial mass is a no-no. I guess I'm going to have to continue next time. Where we simply say that we'll stick in another function to get the potential. So, but we're almost there. T invariance and so on. So all the fundamental principles, the bottom line is, I hope you're impressed by this, that this crazy assumption that there is such a function as the action, this integral of something, that it turns out in the end to be t minus u, and it has all the properties that we associated with it, and we get Newton's laws out of it, all out of that one simple assumption, and all going back to that we can specify the system by knowing the velocities and positions at a given instant. Pretty neat stuff, huh? So, you know, it may not make problems easier to solve, yes.
I was just wondering what the name of the book was that we were sort of following.
I took this lecture directly from Landau and Ch1 mechanics.
Okay.
Or is it theoretical?
Addison, Wesley. Yeah, I don't know how many of them there are. Half a
Depends on the
dozen.
publisher.
Oh, they're not, well, there are 9 listed here. Mechanics, classical theory of fields, quantum mechanics, relativistic statistics, fluid mechanics, theory of elasticity, electrodynamics of continuous media, and physical kinetics.
Right.
They're all beautiful books.
Yeah,
Some more relevant than others in this day and age.
yeah, some authors, I think it's Perelman, or no, Pergamon Press, that splits the book on quantum field theory. It does like quantum electrodynamics and another one.
Uh-huh. Okay. Yeah, I haven't looked at, I've looked at the E&M book, and I used the continuous media book one time. But I don't know the other books. So that's where we're at. And, so as to my unpleasant surprise that this was only a 1-semester course last time, I told